Hi, in this lesson, you will learn about predictive models and how to use them to predict outcomes of future events. As we've discussed in other units, within the field of artificial intelligence, there are subcategories of algorithms. One such category that we've learned about is machine learning. Machine learning algorithms use statistics to help find patterns in data. It then uses those patterns to make predictions and assessments. Machine learning uses supervised learning to help make predictions. Supervised learning is the process of training algorithms to make predictions using testing data, where the outcomes of a specific event is already determined. Programmers give algorithms data so that it can make predictions based off the data it's been trained on. Existing data is provided to the algorithm by the programmer, and the supervised learning algorithm then finds patterns in the provided data. In this case, it makes a line of best fit. While this makes sense in principle, how exactly do these algorithms work? How do they create these models? Many supervised learning algorithms use a mathematical model called linear regression to make predictions about data. Linear regression attempts to create a linear relationship between the inputs in an algorithm to the expected output. With the existing data, linear regression creates a line of best fit, which is used to make predictions. Let's try to understand this by first looking at an example. Data used in a linear regression can often be represented using a graph. As you may have learned in algebra, the x-axis is reserved for independent variables. These are variables of data points that shape and impact the outcome of a model. In our example, we'll use movie ticket sales. The y-axis represents the dependent variable. This variable directly depends on the independent variable. In our example here, popcorn sales are directly affected by movie ticket sales. This means that there is a relationship between both variables, and that as the value of movie ticket sales changes, the value of popcorn sale is likely to change as well. If we were to populate this graph with data points, we can begin to see a relationship between the variables. As the number of movie ticket sales increase, the number of popcorn sales also increases. Because this data is readily available, it can be used in linear regression to determine a line of best fit. The line of best fit is the line, or linear equation, that best expresses the relationship between all data points. A line is considered to be best fit if it has the smallest total distance between each data point. For example, if we were trying to approximate a line of best fit, this would probably not be the line of best fit because the distance between some of the points of the line is pretty significant. Think about it this way. If the line is supposed to represent a predicted result, the distance between the actual data and the predicted result need to be pretty close in order for the line to be best fit. Since the actual results are far away from the predicted results, the line must not be the best fit. If we attempted another approximation, we could see that this is a better fitting line, as the distance between the predicted results and the actual results are much smaller. While we can make approximations visually to determine the line of best fit, linear regression is able to determine the line of best fit using a cost function referred to as the least squares method. The least squares method is a statistical formula that's able to determine the total distance between all data points and their respective place on the predicted line. Linear regression starts by approximating a line of best fit, and then uses the least squares method to iteratively determine which line has the minimum distance between all points. The least squares method is referred to as a cost function. We will explore this more in a later lesson. Using the least squares method to determine the lowest cost line of best fit, linear regression returns a linear model that represents the line of best fit. This linear model often resembles a linear equation that you may have seen in math. Y is equal to mx plus b. These linear models follow the same format as the ones you've seen already. The y value represents the dependent variable. M represents the slope of the linear model. This determines how steep the line is, or how much a dependent variable changes compared to the independent variable. The slope is also referred to in machine learning as the coefficient or gradient. X represents the independent variable, and B represents the y-intercept, or the value of y when x is 0. In machine learning, this term is also referred to as the bias. When a linear regression algorithm is called on a dataset, it creates a line of best fit with real values for the coefficient, or slope, and the y-intercept, or bias. This equation can be used to make predictions about new data that is input into the model. For example, if we were interested in knowing what popcorn sales would look like if 200 movie tickets were sold, this data point could be input into the linear equation to predict the result. Since x represents the independent variable, we can plug in 200 into the model and calculate the value of y. The end result here is 415. This indicates that the linear model predicts 415 bags of popcorn will be sold if 200 movie tickets are sold. It's important to note that the number that is predicted won't always represent the exact number of bags sold if 200 tickets are sold. The line of best fit is able to provide realistic predictions because it attempts to fit the data as best as possible. But even in the graph above, it's clear that some data points exist above and below the predicted line. While results of a linear regression provide accurate results, they don't always predict the future. While linear models are a powerful predictive tool, they have some limitations. For one, linear regression can only be used on data that has a linear relationship. That is, the independent and dependent variables increase or decrease at similar rates. It also works best on data that has a strong correlation. This is something that we'll discuss in a later lesson, but for now, just know that linear models work best on variables that are related to one another in some way. And lastly, outliers in data, or data points that stray away from the given pattern, can impact the line of best fit, causing the accuracy of the model to decrease. Now that you've learned a bit more about linear regression, now it's your turn to check out some examples.